my friend and colleague Rishikesh Kamalaporkar asked me if I wanted to organize a special session at MTNS this year. MTNS is an annual conference on the mathematical theory of networks and systems, and it's where a lot of people from all over the world come to discuss advances in dynamical systems theory. MTNS hasn't actually met since they postponed and ultimately canceled their 2020 conference, and they refused to do anything hybrid or online back then. I didn't think it would actually run, so I said, sure, why not? And we got about 6 people on board to hold a little session. Then, surprising me, our session and our abstracts got accepted and the conference was actually happening, which meant I had to fly to Germany and give a talk. I'll show it to you at the end of the video here in a minute. It's about dynamic mode decompositions if you haven't heard of them before. My wife, after we had been locked away and not traveling since 2020, wasn't about to let me travel on my own. And we can't just leave our children alone in the house, so we brought the whole family. It was kind of a thing. Pro tip, if your 4-year-old starts to get upset, hand them your GoPro and tell them to start the vlog.
Pointing at me. Hi. Pointing at mommy.
Hey!
Bayreuth is a cute town in Bavaria, Germany. Its population is about 75k, and that population has been super stable for about the past 20 years. There isn't a whole lot to do there, but it has a cute downtown, a lot of vegetarian-friendly restaurants, and one-to-one gigantic scale models of dinosaurs hidden behind all these buildings. This little pocket was amazing for my children. My walk to the university and the conference put me through this park every single day, and after traveling from sweltering Florida, this made me 90% convinced that I want to move here. The University of Bayreuth was founded in 1975, so it's a relatively young university, and it's doing very well for its youth. Significant to the work that I do, it is also the home of Holger Wendland, whose book on scattered data interpolation I recommend to all of my students to read. So here's a talk that I put together. It's about how to rig up a data-driven routine for higher order dynamical systems, where we take cues from Koopman-based dynamic mode decompositions. Now, I'm just a guy with a little camera, and in my hurry, I didn't bring a fresh battery. So the recording stops around 1 minute from the end, and I'll fill you in on what happened when we get there. And before I get into it, I would like to thank everyone that agreed to give a talk in our session, and also everyone that attended the session itself. I got to speak with several people afterwards, and it made the whole trip worth it. Now, if you want to see more math content and other things like that, please take a moment to subscribe, and I'd love to hear from you if you want to drop a comment down below that like button. So cheers, and why don't we go ahead and get into it.
For our next talk, we have Dr. Joel Rosenfeld from the University of South Florida, and he's going to be talking about some higher order dynamical mode decomposition.
Yep. Okay, yeah, hello. So as he said, I'm Dr. Joel Rosenfeld. I am from the University of South Florida. That is over in Tampa, Florida, in the US. So it's a bit of a trip to get over here. In any case, so what I'm talking to you about today is dynamic mode decomposition for higher order dynamical systems. And so this is mostly an operator theory talk, and we'll throw in bits of dynamical systems here and there. And I'm going to give you an overview of dynamic mode decomposition because this is the first talk today that's going to be talking about that. So if you have no clue what DMD is, hopefully you'll have some idea. It involves composition operators and a couple other things. And we take a step away from composition operators, and I'll show you how we do that in the latter half. If you want to see a YouTube video that covers a lot of this stuff, I've given a similar talk back at SEAM a couple years ago, and the YouTube video for that is there, and my YouTube channel. If you want to go and subscribe, I'd really appreciate it, and smash that like button. That'd be great. Anyway, so dynamic mode decomposition is basically this. You take snapshots of a dynamical system of some kind, and you break it into what are called dynamic modes, and then you recombine these dynamic modes and to basically reconstruct the dynamical system. So basically you can do some sort of like reduced order modeling, just take the best modes and try to rebuild your system that way. And so it's a really great way to take data and get a model out of it. And there's a lot of operator theory that goes in behind it, which is what makes it really interesting for me. So again, this is a QR code for this video here. That is Spider-Man in the background. I am a bit of a Spider-Man fan. In any case, these are my funding agencies that are helping support this. Mainly this is done by the AFOSR YIP, but also we have other support from another AFOSR grant and also the National Science Foundation. This conference knows what dynamical systems are. Basically, they're differential equations, usually governing some sort of physical system of some kind. And what we are concerned with is what happens when you don't know what it is. And so there's a lot of cases where that could come up with. So for instance, we've done work looking into like unknown ocean currents, wind dynamics. You could have adversarial actors that will change your dynamics, and you'd like to be able to like figure out what's going on there. All sorts of mechanical unknowns that you might make it so like a parameter is missing or something like that, like a length of arm, other things. Friction might change if you're not oiling your system well, et cetera, or a damage component. My main tool here is reproducing kernel Hilbert spaces. So reproducing kernel Hilbert space is a Hilbert space of functions over some set X, and what makes them significant is that they have what we call the reproducing property. And this comes from the fact that their evaluation functionals are all bounded. And if their evaluation functional is bounded, then that means by the Riesz representation theorem that there is going to be a function that represents that functional through the inner product of the Hilbert space. So that means if you take any function in your Hilbert space and you take the inner product against this kernel function, the result that you get is the evaluation of that function at the center of that kernel function. And so, and we call these reproducible kernels because they reproduce function evaluation. Anyway, so each kernel function, they come with a feature space. This is something that machine learning people really like. They usually think of talking about these sort of like infinite dimensional like vectors, and then they can take inner products of them by evaluating the kernel function. That's not really what I do, but that's what a lot of people in DMD actually look at. And a typical example of a kernel function is the Gaussian. So the Gaussian radial basis function is a kernel function, and wherever that hump is centered, that is the center that kernel function reproduces. So this is a space of real analytic functions and is closely connected with the Fock space. So there's something else that we're going to talk about a lot. And these are occupation kernels. And so if you're given a continuous trajectory, then an occupation kernel basically will reproduce this functional where you take the integral after composition with your trajectory for any sort of function you have. And they have a nice clean representation in terms of the kernel function itself. And this allows us to access a lot of continuous time dynamics and avoid discretizing our dynamical system, which really is important for a lot of things that we're going to be doing later. So what if we don't have a model for our system? So we're trying to learn this dynamical system. So this is DMD 101. So what we're going to start with is a collection of snapshots, so x1 through xm. And the idea is we want to use this in order to get a model for the system. And traditionally what you do is you stack these vectors as x1 up through xm minus 1, and then you think there should be some matrix that should map you to this other side of just this shifted matrix. And so then the idea is that if you take that, if you find that matrix A, then you know exactly how to, you have a model for your system. At least it reproduces exactly what these guys are going to do. But this is limiting because if your system is, say, two-dimensional, then you have you only have 2 rows, and that makes A basically have rank 2 at most, and so it doesn't have a whole lot of flexibility. So ultimately, you turn to what are called Koopman operators. Koopman operators operate over a function space, and so and they operate by composition. So you think of your system as a discretized system, and so basically then you're thinking of this discrete system, and you throw in your discrete dynamics as a composition. And what that does is that inside of what we call observables, which are the functions in your function space, what it ultimately does is it the composition operator, if you apply that to an observable and evaluate xi, then it will advance xi to xi plus 1 inside of the observable itself. And so if our Hilbert space is a reproducible kernel Hilbert space, you can take advantage of this, and you can even see that it actually shows that the composition operator, this Koopman operator, if you apply the adjoint to a kernel function, then it advances the center of the kernel function. So that gives you a sort of operator level sample of the Koopman operator. And so we basically use this in order to build an approximation. So the goal of DMD, so for Koopman operators, basically if you take the eigenfunction of a Koopman operator and you do this whole advancing sort of thing, basically what you can see is that for each index out of our snapshots, you can strip it out and it comes out as a lambda. So basically you start with a phi applied to xi plus 1, and you can pull all those I plus 1s out as lambdas to I plus 1, and what you're left with is phi of x naught. And so in particular, even if you have a nonlinear dynamical system, your eigenfunctions will more or less view it as a linear system. And so you basically get this as a, so basically you try to express things in terms of these eigenfunctions because you know exactly what they're going to do as long as you're looking at a snapshot of your system. But the thing is, we don't have access to the Koopman operator. The Koopman operator comes with the dynamics. We don't know the dynamics, and so we have to build a finite rank approximation. We build a finite rank approximation, and so our goal is to not exactly find the exact eigenfunctions, but we would like to find approximations of eigenfunctions, and that's really what DMD does. You'll see a lot of DMD papers talking about finding invariant subspaces and things like that, and if you can, that's amazing, and you'll do it, and that's great. But in reality, we're just dealing with some arbitrary data that we found from a trajectory, and the best you can do, or really hope for, is a really good approximation of those invariant subspaces. And so ultimately, this is how that approximation is going to boil down. You're going to have some epsilon term there, but they'll more or less pop out these lambdas as you like. And yeah, I mean, so it's more or less big O of epsilon is your error as long as you don't let I get too big. And so that's more or less where that is. So we would like to, that upper right-hand corner, we would like for it to be true for all x. You know, if you use ergodic methods and things like that, you only get that true for almost every x. But there's a really nice thing about reproducible kernel Hilbert spaces is that norm convergence implies pointwise convergence. So if you can show that you can get that quantity up there, not in absolute value, but in norm to be small, then you also get the absolute value to be small as well. And so that's why we really like using reproducible kernel Hilbert spaces, and that's the real reason why you need to use reproducible kernel Hilbert spaces in this context. All right, so simple algorithm. I don't want to take too much longer on this because it's not even the point of the talk, but I want to give you an idea of what's going on here. So basically what you start with are observed snapshots, and you build a finite dimensional subspace out of the kernel functions corresponding to them. And then basically what you're going to do is first you're going to assume that they're in the domain of your possibly unbounded operator. We could actually work with the adjoint instead, but it's just easier to do it this way. So basically what you do is you take a look at what their Koopman operator does to each one of these kernel functions. So you take your kernel function, you apply the Koopman operator to it, and then you project back onto the span of kernel functions, and then that way you have this operator that maps from the span of your kernel functions back to the span of your kernel functions, and then you can look for eigenfunctions there. And the idea is that as the kernel functions, as you get enough sample points, then since kernel functions will span the Hilbert space, eventually this operator should, in principle, be able to approximate your operator. But if it's unbounded, then you have finite rank approximations. There's other issues. I have a whole other paper on that one. But yeah. So basically, this is your approximation, and we try to get approximate eigenvalues. And what we do is we take this thing called the full state observable, which is basically sends x to x, and we decompose that in terms of our new eigenfunctions. And if you do that, then what's really cool is if you feed in xi into your full state observable, which then feeds into this approximation, this expansion, then you get a model. You get basically a linear combination of exponential functions. And so that is the magic of DMD, is by doing this whole process, you basically get a model for your system, for your unknown dynamical system, and in fact, this model looks a lot like the sort of model you get out of a linear system in general. Occupation kernels. So this is a really cool animation I put together. So an occupation kernel, it's related to kernels, and essentially, this is that thing that's going to be doing reproducing this sort of integration. Oops, there we go. Integration by after composition with a signal. And so what's really nice is that if this functional is bounded, and it's usually bounded as long as you reproduce the kernel Hilbert space, it consists of continuous functions, then there is then by the Riesz representation theorem again, there is a function that represents this functional through the inner product of your reproducible kernel Hilbert space. And so yeah, we call this thing an occupation kernel. That corresponds to the signal theta. And so you can actually just figure out exactly what it should be if you, as far as function evaluation, if you just take the occupation kernel and you look at what it should be at, say, a state X, then you turn that into an inner product through the reproduced kernel Hilbert space formalism, and then you just swap those around. I'm working over a real Hilbert space, so I don't have to worry about conjugates, but that works too if you need to. And then basically you get this whole chain here. So ultimately the occupation kernel is more or less the integral of a kernel where you just move the centers along your signal or your trajectory. And this here is an example that you get when you have a spiral trajectory. And I always thought that looked kind of cool. So now what do you do for continuous time systems? So with the Koopman operator, what we were doing is we discretize the system first. And since we discretize the system first, that actually eliminated the possibility of looking at a lot of systems that have, say, finite escape time and other issues. And so we looked at these sort of level operators, which are really connected to what people call the Koopman generator. And so you start with a continuous time system, and we don't want to discretize it. What we're actually going to be doing is we're going to be moving the sort of discretization onto this occupation kernel, where the discretization there is really just how well you can take an integral, and it's not happening on the operator level. This operator is the gradient of G dot product with F, where F is your n-dimensional dynamical system. And if we actually have a trajectory of the system, then you actually have this really nice relationship between this operator corresponding to the continuous time dynamics and the occupation kernel. And in fact, what you can see here is that if we put this trajectory in there, then what happens is that we basically get this f of gamma of t, but that really is just gamma dot of t. And so this whole thing just becomes, by the chain rule, you can turn it into the time derivative of g composed with gamma of t. And then the fundamental theorem of calculus gets you, that's just the difference of g evaluated at the endpoints of the trajectory. And then by expanding this, you get g interproducted with the kernel functions corresponding to those same points. So that tells you that the adjoint of this unbounded operator, this level operator applied to an occupation kernel where the trajectory matches the dynamics, then you get a difference of kernels, and this gives you an operator level sample, just like what we had with the Koopman operator. And so basically, we also have this nice relationship for eigenfunctions of this operator, and it basically does exactly the same thing. If you put a trajectory in there, an eigenfunction will see that as a sort of exponential function as well. And so that's really nice. And so it's just like what happens with the Koopman operators, just sort of in a continuous time case. And so we have a paper here, and that is published in the Journal of Nonlinear Systems, I believe. So in this case, our data now comes in trajectories. You could just have a whole bunch of snapshots, and you just truncate them into different trajectories if you'd like. And that's more or less how you get that. And basically, this is the finite rank approximation you get. It looks a lot like what happens with the Koopman operator. And in fact, the whole principle of building this is exactly the same. So yeah, so the idea is that we find eigenfunctions for this. Okay, I guess the audio was running on that. I apologize. Anyway, I wish there was a way to kill that. Any case, so basically a really common example that we run into is the cylinder wake example. And in this case, these are what we call Liouville modes, and these are what we recombine in order to get reconstruction of the things we see. And at the last conference I was at, they actually had this neat little bubble machine with all these cylinders inside. I'm like, that's it. That's the thing. So I actually ran out of the conference area, took a quick picture, and then like threw it in my slides real quick. That's what you do for first order dynamical systems. And a lot of times, if you want to take analyze a second order dynamical system, you'll turn it into a first order dynamical system. And you do this if you even just want to run simulations, right? You want to do Runge-Kutta on this sort of thing. You basically change your second order or your third order dynamical system, and you just stack the vectors of like x, x dot, x double dot, etc. And then you basically turn your your higher order system into a first order system. But from a learning perspective, this is really, really bad. And the reason for that is known as the curse of dimensionality. So, the curse of dimensionality basically says that the number of basis functions that you need in order to get a good approximation of something increases exponentially with the size of the dimension of your system. And so a lot of people do the state augmentation in order to do this, and they either use, they either use this sort of thing where they'll take numerical derivatives and basically which has its own collection of problems, to do state augmentation from data that they've seen. And numerical differentiation is really sensitive to signal noise. And so that's not always the best way to go about it. Another way to do it, which avoids this, is to do time delay embedding. So you take one spot, and you take one snapshot, and you take the previous snapshot, you sort of stack them together, and that will also do that. And so this is another way you can do this with a second order system if you still want to get something out of it. But in both of these cases, you have effectively doubled the dimensionality of your system. If your system was already 5-dimensional, now you're working with a 10-dimensional system, you would have already had trouble with getting a good approximation of a 5-dimensional system. Why would you want to do 10 dimensions? I mean, that's pretty bad. So our objective is to avoid this state augmentation, and so we introduce a new operator. So what we're going to do is we're going to go take a look at what actually happened when we looked at the first order systems, where that operator even come from. So that operator that we were working with really just came from taking the composition of your G with a trajectory of your system, and then you take the time derivative and you use what you teach to Calculus 1 students. Basically, you just use a chain rule. And then you recognize that x dot is equal to f of x of t, and then you replace that with f. And that's great. That gives you this operator, and then you get this nice property of the eigenfunctions. But what if you have two derivatives, right? You can even do this with 3 or 4, but just for example here. And so here, if you take two derivatives of g of x of t, you basically get this. And so you end up having a Hessian working its way in there, and then at least two different state derivatives. How do we make this into an operator? So what we do is we take a look at the x dots and we replace them by the integral from 0 to t of our dynamics, our f. And then we take x double dot, replace that with f, and that's fine. And then we make this sort of second order operator. And you'll see, I forgot to transpose on that first integral, but you get the idea. And so then basically what we end up having is we end up having a non-local operator. This becomes a bit of a headache. Actually, it's such a big headache that about half of the paper that we wrote is just to deal with how to define this thing well. But basically, if you need to start working with functions that take signals to signals rather than states to states. And when you do that, then you can take a look at your signal, you can take a look at all previous values from the current time back to the start time. And so then your observables change slightly, and we move from reproduced kernel Hilbert space to something we kind of made up, which was a single valued reproduced kernel Hilbert space. And in this case, 2 minutes? Okay. And in this case, it's a vector valued reproduced kernel Hilbert space with an extra veneer on it. But what's nice is that if you have an eigenfunction for this new operator, you basically get this. And so it's not quite exponential, but it's a linear combination of exponential functions. And that's really nice too. What's interesting is that we only have one point, gamma dot of 0, that we need to actually approximate a derivative for, which is much better than doing it for, say, the entire trajectory. So the algorithm is more or less this. You take your trajectories that satisfy your second order system. You introduce a new occupation kernel. It's more or less the same thing as I said before. It just has this extra t minus tau in the middle of it. Don't worry. And we can just ignore that. This comes from doing iterative, as Cauchy's formula for iterated integrals. And then we have another sample of our operator by taking the adjoint of this operator to this new occupation kernel. And it's in terms of a bunch of kernels of kernels on top of each other, but that's just single valued stuff. Don't worry about it. We get a finite rank approximation. We can decompose our full state observable with that. And basically, the top is our finite rank approximation, exactly the same setup as we had before. It's just Hilbert space, so projections and whatnot. And then on the bottom, we have our expansion of our full state observable, and this C of m comma m are our second order modes. So we did a couple of examples with this. Really simple system. First thing you would ever want to try it on is a linear system, which isn't really the point of this thing, but we want to know at least that works. And so you can't even see any difference here. I mean, like there's a very, on the right-hand side, just because of time and slight errors, it builds up and you get a little bit of a difference on that side, but more or less, we get this whole sinusoidal trajectory just like what we want, which is nice. And so here we just use a bunch of sinusoids in order to build it as our trajectories for our occupation kernels. And here we did it with a beam where it was fixed on one end and let to move on the other end. And you can see the error does increase with time, but that's just sort of natural with any sort of approximate method. And, but it does start pretty small as far as the error goes. Generally speaking, you only really trust these DMD methods for short time horizons. So that's okay.
When I got back to the camera, I saw that it cut off. I was terrified that I lost the whole thing. But in the end, it was really just one slide. And that slide was an animation that Rishi put together to illustrate the beam example at the end. And basically, because it stayed more or less that blue color, it meant that our method worked really well over time. And so we didn't have very much error. Anyway, so then after that, yeah, thank the audience for coming, and yeah, that was the talk. So my time in Bayreuth was a lot of fun, and I'd really like to go back sometime if that was possible. I got an opportunity to talk to a lot of people about dynamical systems theory, Kuban operators, things like that, and also a bit about kernel spaces. And if I told you I was going to send you an email, don't worry, I haven't forgotten. Immediately on coming back, I got COVID, and then we had a hurricane come through, so it's been a little hectic. So some things coming up on the channel is that we have some more analysis 101 videos. There's a metric space video I'm working on now, and I'm also working on another control theory video on layup and off functions, and that is critical for showing stability of nonlinear systems. And then there's also a couple of fun videos that we have coming up. Anyway, so I'll put a video right here for you to go check out on DMD if you want to know more about that. And otherwise, I hope you have a great day.